Hi there, this is Ayush from Lightscline. Uh, I'm gonna talk about Lightscline Compute in this video and the contact information. My contact information is present on the screen. You can scan the QR code to reach me via LinkedIn. Uh, so let's start with the assumptions of this package. So the first assumption is the data has to be stored in a central place. That means we do not have the ability to take the data from distributed sensors. That you have to take the data from multiple channels or multiple sensors into in a one place, and then you have to make sure that the data is synchronized. So that's one of the first assumption that we make. The second assumption is that the data has to be labeled for this package. Now if you have unlabeled data, which is most of our customers, we do have solutions to help you label those data points, and we do have solutions to work on them end to end. But Lightscline Compute is not for that, so I'm not going to be focusing on that. But if you do have any of those use cases, feel free to reach out to me. Uh, Now, the next point in this is going to be data ingestion. That means, uh, so the first line that you will write, which involves Lightscline Compute, is going to be something like this, where you're going to ingest a lot of data in it. You can either ingest single channel data or multi channel data. In case of single channel data, the data would look something like this. You have a block of data point. This block would increase if the time goes on. So if we expand this to the multi-class thing, this is how multiple classes are going to look like. So this was basically a 2D list where each of them is like one class. Each of the bars is one class. Therefore, if you give a 2D list instead of data, you should get the uh, that is fine. Uh, if you're giving a 2D list, your fs should also be it should only be one number, because you are dealing with single channel. You The sampling frequency of each channel should be same across classes, so make sure that is the case, otherwise you'll get an error. Similarly, uh, if you have an imbalance in your data set, so if all the classes do not have uh, equal data points, then that's fine. That is an acceptable form of input. Therefore, we require you to give a Python list rather than a 2D numpy or something like that. That being said, we know that Python list is slow, and we can work together on ingesting the data directly into the package. Let's talk about multi-channel data. This is how the multi-channel data would look like. Each of these colors is one channel of data. And yeah, if you collect more data, this length of this whole block is going to increase. This is on an inference time. So the training would look something like this, where one block might correspond to one class, second block might correspond to another class. So this is basically a 3D data. Uh, you would use the same line of code for multi-channel data as well. This also supports multiple sampling frequencies. That means because you have multiple channels, that doesn't mean that all the channels should have same sampling frequency. You might have vibration sensor and pressure sensor and temperature sensor. All of these three sensors do not sample at the same frequency. Yeah. So that is supported. In that case, please give a list of sampling frequencies for each channel. That's all we ask. Uh, there's one mistake that a lot of customers make. So I want to clear that up here. When you're gonna ingest your data, so let's take an example. In one of the examples by us, which is given in our GitHub, uh, what happens is we're talking about a human activity recognition use case. The first activity might be standing. The second activity might be sitting. So someone might be like standing and then he or she sat down and then they stood up again. Uh, in this case, how do you handle the data? How do you give the data to Lightscline? The obvious answer that comes to, or one of the answers that would come to your mind is do something like this, where you have activity and then so basically you might take all activity 1 as class 1 and then all activity 2 as class 2. So you might give the data in this case. But do you see a problem in this case? This is not the ideal way to give the data to the package. The problem is you would have some kind of discontinuity in the intersection of it. Now, if these blocks are too big, like if you have only 2 or 3 discontinuous breaks, that should be fine. That should not matter. Uh, but if you have a lot of discontinuous data, I would advise another way, which is give data some like this, where you have activity 1. So you are separating the blocks of data and then you are giving a class corresponding to each block. This would ensure that the package does not do something with the discontinuous part of the data. So to do that, make sure that you also give labels. Now, once the data is given to the package, the second line of code would be reduce and preprocess. This is gonna preprocess the data and then reduce the amount of data. I'm gonna talk about, let's start with preprocessing the data. Now, uh, one of the parameters that you see here is window time. So I'm gonna explain what that is. So what we do is when you give us the data, we create windows of it. So like each window would correspond to one label, which is the class it belongs to. And you can control the length of the window by window time. So if you increase window time, uh, so if you increase this to, let's say, 10 seconds, you're gonna collect more data. What does that lead to you? That leads increase in latency. That means uh, you would have to wait 10 seconds at inference as well, which might not be uh, what you want. So if you have a very big window time, that's bad. But if you have too small of a window time, you might not get the accuracies that you want. So choosing this window time is crucial trade-off between accuracy and latency. Uh, we also offer data augmentation inside the package. So what data augmentation multiplier does is it basically, so if you have like uh, 1 megabyte of data, this would make it 360 megabytes of data, something like that. So it's like a multiplier. Uh, so to understand what happens behind the scene, you have the data. Let's say you are performing windowing on it. Uh, what happens is when you have this on, you have overlapping windows on it. So this because you have overlapping windows, the number of windows increases. Because the number of window increases, the data increases. Having a higher data augmentation multiplier is good when you want accuracy, but having it higher also means it needs more time in training. So because you're basically increasing number of rows, that means the training time would increase. So this is a trade-off between accuracy and training time or training time, not testing time. Uh, that would be ideal for like if you have a lot of cloud compute and you just want the best model out of it. So you can have it in a very high number. Typically, it won't be as high as 360, but in this particular example, we had two less, like the data points were not enough. So we had to augment it a lot. That's why this is such a high number here. This is another example of like how the windowing would happen for the whole thing. The next thing is data reduction. What we do is let's select one window af- after windowing and uh, augmentation and stuff, we take one window and then we reuse that window itself. What does this do? This ensures that there's no there's no place in data where we are losing some kind of information. That means each window, so if you have a class, an anomaly kind of thing, we are not going to lose that information because the reduction happens in each window. So we are going to take we are going to train on all the windows, but not all the data points. That's the difference. And again, uh, basically what it means is we have like three channels here. All the channels inside the window would also be undersampled. Uh, yep. Again, having this percentage reduction higher would require would would basically result in training the model. Like if you have uh, 80% data reduction, that means it only works on 20% data points. If you have 0% data reduction, that would mean like you're using all the data for training and all. That is going to be slow, so don't do that. But we have seen typically around 90. uh, Anything above 80 is good. That should give you enough accuracies, but if you do something like 90, 95, depending on the use case, you might get same accuracies as like 100% data. So uh, keep this number above 80. That should be good. Training the models. So this is how one window would look like. Now to train the models, what you would do is we would take all the windows, stack them, and then basically one window would basically be like a column, and the number of windows would be like something like a row. Uh, so this is like that. This is how the data would be there before training. Now, uh, when you pass it through model training, we want to make sure that the reduction happens and the neural networks knows about it. So we want to make sure that, for example, the position and coding is captured. We want to make sure that the shift invariant is captured and stuff like that. So uh, that is uh, all of this would happen with just one line of code. So this is the third line of code you would write, which is this. You don't have to worry about how do you handle all of that. That is handled by the package. So as long as you only have to care here, you only have to care about the number of layers in the model. So if you have a lot of windows, that means if you have a larger data set, or if you are using a bigger multiplier, data augmentation multiplier, the layers would go higher. That's on the model training side. Model prediction. So let's say uh, you had a you before giving it to Lightscline's package, you actually uh, decide did a X train and X test split, uh, and you want to do a prediction on X test. You can just call this line of code and you should be good. But what basically happens behind the scenes is we'll take that block X test, we'll do the same pre-processing. So we'll window the data. We're gonna uh, reduce the amount of data in each window, and we're going to give you the output for each window. So instead of having just one number, you're going to get in this case you're going to get three numbers because you had three windows on it. So don't be surprised if you get like multiple outputs from one X test. uh, you can like do a mod operation, something like statistics.mod, to get just one answer. But again, this is not ideal on a production environment where you want to monitor each window, because that would be a real-time operation. And then if one of the windows has an anomaly, you want it to be like flagged or alerted or something like that. I think that's pretty much it. These are the four lines of code that we use. Uh, if you have any questions, shoot shoot us an email at info@lightscline.com or ayush@lightscline.com or anything. Uh, we would be happy to help you with your implementation. Thank you.